Okay, now we will start a new chapter. It's about basics of enumerative combinatorics. So we will learn some necessary properties in enumerative combinatorics that will be used later when we study orthogonal polynomials. So from now on, I'm going to use this notation. And the first section is formal power series and generating function. Okay, so what is a formal power series? So in your calculus, you'll probably learn this, a power series. What is a power series? In calculus, power series is a series of this form. Fx, usually we write fx and a0, a1x, a2x squared, like that. So it's an infinite sum, so it's a series. And we say that in this case, each an is called the coefficient of x to the n in the power series fx. And a0 is called of course the coefficient of x to the n, but it's also called the constant term of fx. And this is common terminologies in formal power series. And when we and if these numbers, if these are real, then we can think of fx can be considered as a function defined on a set of values, set of x, for which the above series converges. The series converges. So we say like the radius of convergence and the interval of convergence, things like that in calculus. So for example, if the absolute value of x is less than 1, then we can write 1 plus x squared like that. Is a 1 over 1 minus x, called a geometric series. And this is a valid identity for all x, real numbers x whose absolute value is less than n. This converges, and this, if you compute this, this is equal to 1 over 1 minus x. But this doesn't make sense. If the absolute value is not less than 1. But in the language of formal power series, this works without needing to mentioning the range of x. So to define formal power series, we will first fix some notation. So let R be a commutative ring with identity. And if we want to divide some elements, we will often consider R as a field. And R of x bracket square bracket x is the ring of polynomials in x with coefficients in the ring R. So the usual polynomials are here. So we have polynomials, and then we can add them, multiply them in the usual way. And now we can define formal power series. So the ring of formal power series with coefficients in R, our ring R, is as a set, is the set. We write the notation is we use a double bracket, and this is exactly like this in a power series. But okay, so let me write this down. So it's a series, infinite series like that, where the coefficients are all in the ring. So they are ring elements, and because this ring, we have to define what the addition and multiplications are. With addition, so a power series, and from 0 to infinity, a n x to the n, we have one formal power series and another formal power series like that. Then we can add them. The definition is we just add coefficient wise like this. This is the definition of the addition and multiplication. So we multiply two power series, formal power series, I mean. And this is like the way we multiply two polynomials. This is exactly the way we multiply two polynomials. K to n, ak, bn minus k. So in other words, if you want to multiply two polynomials, and then what you do? You select one term here, and multiply them, and then that's going to be one term in the product. So it's exactly the same thing. The only difference is we have infinitely many terms, but this is still well defined. For each x to the n, we get only finite terms here added. So this is the definition of the ring of formal power series. So roughly speaking, so formal power series are basically, you should think of this as polynomial, just polynomial, because that's the terms that are that we are familiar with. So you should think of formal power series as polynomials with infinite degree. That's the only difference. So if the degree is finite, it's going to be a polynomial, otherwise a formal power series. So in fact, formal power series contain polynomials, because if you have only finitely many non-zero coefficients, then it's going to be a polynomial. And there's a multiplicative inverse. There's multiplicative inverse is just 1. So 1 means 1 plus 0x squared, like that. So this is a formal power series, which we will just simply write as 1. And if you multiply any formal power series to this, then you get just itself. So it's a multiplicative inverse. That is not multiplicative identity, yeah, right? So the multiplicative inverse, so the inverse of f of x formal power series is another formal power series g of x such that fx gx equals 1. And of course, this is defined if such gx exists. Otherwise, there is no multiplicative inverse. So not every formal power series has multiplicative inverse. But if there is, then we define the multiplicative inverse to be this. So we write in this case f inverse, oh sorry, not this inverse, or 1 over fx for the multiplicative inverse of f. Okay, so this is the notation. So let's see an example. So okay, let's copy this. This is true, and on the language of formal power series, this holds. So see, we don't say anything about the range of x or whatsoever. And this is because the reason why this is true is if you multiply, okay, because if you multiply this formal power series and 1 minus x and see what happens. So you just expand this, then the distributive law still holds. So it's 1 minus plus x squared. If you expand this using 1, then otherwise if you multiply these to every term over here, then you get x plus x squared plus ... So everything cancelled except the first one, which is 1. So you multiply this formal power series and this formal power series, and you got 1. That means the multiplicative inverse of this formal power series, which we denote minus 1 to the minus 1, this is 1 minus x, right? Equivalently, this is also the multiplicative inverse of this. So we can say this, and the multiplicative inverse of 1 minus x is 1 plus x squared plus ... But this is the same notation as 1 over 1 minus x, so that's why we have this. So this is true because this satisfies the definition of the inverse of a formal power series. And one thing that important you need to remember is this important aspect of formal power series. This is something that you always have to remember, is that the coefficient of x to the n must be computed in a finite number of additions and multiplications. So what do I mean by that? Example, let's consider e to the 1 minus x. I mean, this is just a definition. So by definition, let's write like this and factorial. This is the usual way we expand this in calculus. So this let's consider this infinite series. This is not a formal power series. This is not a formal power series. In this ring of formal power series with the real number, real coefficient. Why? Because the coefficient, the constant term, which is the coefficient of x to the n, is what? So if you expand this, you have 1 plus n x plus dot dot dot. So you have 1 everywhere for each n. So the constant term is summation n from 0 to infinity 1 over n factorial. Cannot be computed. It's infinite sum. So this cannot be computed in a finite number of addition or multiplication. So that's why it's not a formal power series. But let's compare with another example. But strangely enough, e times e to the x, which is exactly the same in calculus, but this I define e times x to the n over n factorial. This is a valid formal power series. In this. Why? Because every coefficient x to the n is, maybe I can say because every coefficient is just e or 1 over, maybe it's not a coefficient of x to the n, let's say, that's more accurate. Coefficient of x to the n for every n is this, which is just a real number, right? We don't have any infinite sum here. So this is a formal power series. So you have to be careful here. So these two are the same, exactly the same as functions in the real, as a real valued functions. But if you consider this as a series, this is not a formal power series, but this is a formal power series. So when you talk about formal power series, this is really about how we present the sum, the series, not, and we are not interested in this as a function in x. So that's the difference between power series and formal power series. For power series is a function in x, but formal power series is just a ring element, formally defined ring element. Okay, so now we know how to add and multiply two formal power series, but there's another operation. So for two formal power series, say fx and gx, we can define, but here g0 is non-zero, we assume that. Define the composition of f and g by this. So the notation is just f of g of x is exactly like this, where you just replace x by gx. So fn gx to the n. And here, this is an infinite sum, so we have to be careful and we have to check whether this is your valid formal power series. But this is a valid formal power series because of this. Since g0 is, oh sorry, just is the opposite. G0 must be 0 because g0 equals 0. Gnx to the n has lowest power, lowest degree greater than or equal to n. That means every term appearing here has degree x to the n and x to the n plus 1, etc. So we have some coefficient, could be 0, but looks like this. So everything before x to the n has coefficient 0. Because imagine that this is like gn x to the n, gn plus 1, x to the n plus 1, etc. Oh, sorry. No. g1 x, g2 x squared dot 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 raised to the nth power, because g0 is 0. So if you multiply n, that means you have n factors like that, the same factors. You have to select one term in each factor, but every term has degree at least 1 here. So if you multiply n of them, then the degree must be greater than or equal to n. So it has degree, every term has degree at least n. So the coefficient of x to the, say, m in this series is equal to the coefficient of x to the m in the finite sum m. You only need to look at the n from 0 to m, because if you have higher, if n is bigger than n, the degree always exceeds this, so they don't contribute anything to the coefficient of x to the m here. So we have finite sum here. So for every fixed m, you can compute this in the finitely many additions and multiplications. So yeah, that's the idea. So this is well defined. But if m is g0 is non-zero, then coefficient of x to the m cannot be computed finitely many times, finitely many number of computations, because everything here has constant term surviving. So here you have to look at the coefficient of x to the m here. For instance, if g0 is non-zero, for instance, constant term, in the series here in the definition is summation fn g0 and from 0 to infinity, which is infinite sum unless f is a polynomial. So this is not well defined in the language of formal power series. So that's why this is necessary. All right, let's move on. And there is a simple criterion for a formal power series to have an inverse. So let's say in this case, we assume this to be a field because we want to have a division for ring element. A formal power series, fx is a formal power series. Then fx inverse exists if and only if the constant term is non-zero. This means f0 if the constant term, this is the constant term is also written in this way because we don't usually substitute x anything in x, but we do substitute 0 there. So for example, let's see. Here, imagine what happens if x equals 0. These all disappear. So this is the constant term, and that's why we write the constant term in this way. And you can think of this as the same thing as substituting x equals 0 in the power series. All right. All right. So inverse, multiplicative inverse exists if and only if the constant term is non-zero. So let's prove this. So this direction So let gx be the inverse. And just for a contradiction, suppose this is 0 and see what happens. Then the constant term of fx gx is f0 g0. It's the product of the constant term, so it should be this. But this is 0, right? Because this is 0, ring element. But fx gx, what is xx gx? So this has constant term 1, which is a contradiction. Therefore, the constant term must be non-zero. Okay, so the other direction. If the constant term is non-zero, we can just construct the inverse. So let's write fx. The constant term is, say, f0 and 1 minus h of x, where hx is okay, so let me do this step by step. Okay, so let's do this again. f0, f1x, f2x squared. And I'm gonna factor this out because this is non-zero. We can factor like this: f0 inverse f1 x plus f0 inverse f2x squared. So I'm gonna rewrite this in this way: summation. So 1 plus. I'm gonna rewrite this, and for some reason I'm gonna write this as like minus of h of x. So this h of x has only terms, it has a 0 constant term, so we can write this way, where hn is this with minus, so minus f0 inverse fn. So if we define h this way, then this holds. So okay, once we write this, then we can construct the inverse of f. So we want to find the inverse, right? But this, if you write in this form, maybe I can separate these two things: 1 over f0, 1 minus hx. But this looks like a geometric series, so we can write this way. But this is a valid formal power series because h has a 0 constant term. So as we saw before, hx to the n has lowest degree greater than or equal to n. So if you want to compute, say, x to the m, coefficient of x to the m here, all you need to do is to look at just terms up until hn to the m. So you can look at just finitely many addition of formal power series, so you can compute this the formal in a finitely many times of additions and multiplication. So this is indeed formal power series, and this is the inverse of hx, f of x, because if you multiply f of x here, then you get 1. So that's the proof, basically. And there are many things that we can do as we do in calculus. For example, as in calculus, we define the derivative of a formal power series fx derivative of fx, or let's say derivative of fx by, we write f prime x in the usual notation. So what is the derivative, the term by term? So what is the derivative of x to the n in calculus? Is n times x to the n minus 1. And that is the definition of the formal power series, the derivative of a formal power series. But actually, because of this is 0, if n is 0, so we can think of this as n greater than or equal to 1. So it's fine that we write this from 1. That's the same thing. Or I will also just write a 0 sometimes because it doesn't contribute anything. Then many things that hold in calculus still hold here. So proposition, we have this usual differentiation rules like fx gx prime equals f prime x gx fx gx g prime x, the product rule and the quotient rule holds as formal power series. And the chain rule also holds. Prime equals f prime g of x times g prime x. But of course, we have to assume that here gx is non-zero because you don't want to divide with 0. Actually, the inverse of g must exist, so g0 is non-zero. And here, the composition must exist, so g0 must be 0 in this case. Okay, so I'm not going to prove this, but they can all be proved using purely formally, only using these axioms, and we can prove these all. And also this is a definition of the derivative, so using the definitions only, we can prove them all. So these can be useful when we compute generating formal power series and manipulations. We can also consider multivariate formal power series in the usual way. So they are just multivariate polynomials with infinite degree. You can think of them that way. We will see more examples later. And now let's define generating functions. Generating functions are basically formal power series, but they are associated with some sequences. So generating function for a sequence an and from 0 is the formal power series. This just n from 0 an x to the n. So this is nothing but, so these generating functions are really the same as formal power series, but we only have some sequence attached to it. So the generating function for the sequence is just a formal power series. So sometimes we're not going to distinguish generating functions and formal power series, but the basic idea is generating functions record sequence. So generating function is nothing but a way of recording the sequence like this. But instead of just consider this as a pure sequence, one advantage of using generating functions is that we can use many techniques in the formal power series, like derivative, multiplication, and composition, and things like that. So let's see some examples. The generating function for a sequence an 2 to the n is by definition n greater than or equal to 0, 2 to the n, x to the n. But we can rewrite this as 2x to the n, but this is the geometric series, so we can write it this way. So this generating function has a compact form like this. So instead of remembering all this 1, 2, 2 squared, 2 cubed, etc., you can just compactly encode this as a function like this, generating function like this. And let's see if we can compute this. An is n times 2 to the n. Can we find the generating function? And this has some similarities with these two. And if you remember, if you take the derivative, we get something like this. So take the derivative in the previous example, then we get n from 0, n times 2 to the n, x to the n minus 1 equals derivative of this, but we can use the differentiation rule here. So it's going to be 1 minus 2x squared and 2 using the quotient rule. And because we want this an and this is xn, so we multiply both sides by x. Multiply by x, then we get the desired generating function for an, 2x or minus 2x squared. So the generating function for this sequence can be computed in this way. So sometimes generating function for a sequence has a nice formula like this, but sometimes the generating function can be more complicated. And we can also talk about generating function for array of instead of sequence, we can have array like an, m, where n, m greater than or equal to this. Then generating function for this will usually have variables x and y, so multivariate formal power series basically. But instead of introducing that terminology, multivariate or generating function for an array, we will just more generally consider generating function for arbitrary objects, usually combinatorial objects. So let me define that. So the definition, A is a set of say combinatorial maybe, but this combinatorial object will be mostly interested in combinatorial objects. So it can be just a set of any object. The set could be an infinite set. And we define a weight of A is this means set, yeah, is just a function which we denote like this. A to any ring. So it's any ring. It could be a ring of formal power series or anything. So that means you have some quantity associated to each element in this set. Okay. And the generating function for this set with respect to the weight function, Wt, is the formal power series of this form. You sum over all A element in this set A, and you sum the weight. Of course, provided that this is a valid formal power. Yeah, actually, I think this sum is valid, provided this sum is valid. What do I mean by that? If this is a finite set, then it's of course always valid, but it could be an infinite set, but there will be an element in this ring. It could be a ring of some formal power series. If it's well defined in that series, then it's okay. But of course, the examples that we will be dealing with will mostly, this will be well defined. Let me give you some example just to get the idea. So the generating function is really a way of listing the weights of all the elements there. So you, for every element in the set, so for instance, if A has like several elements there, then for each element you associate the weight. Here we have weight, and then you add them all together. And that's basically the generating function. And we will see many examples of generating functions in these lectures. So, example. A is, let's say, just a set of all non-negative integers. And we define the weight of A to be just x to the A. Then the generating function for A, the generating function for A is, of course, with respect to the given weight, is by definition A in A x to the A equals, so we have a 0 there, so x to the weight is 0. Oh, sorry, yeah, this is right. But let me write this step by step. Yeah, just the definition is A, but this is I from 0 to infinity. If I is x to the I, right? If I is in a set A, then the weight is x to the I. So, but this is the geometric series, so 1 minus x. The generating function can be written in this way. And maybe another example. Now let A be the set of all subsets of n. This is the set of elements from 1 to n. And define the weight of element A in this set A. Define this to be x to the A, y to the n minus A. So this A is an element in A. That means this is a subset. So it has cardinality. So this is what the cardinality. This is the number of elements in the set. So this is a number, integer. This is also an integer. So the weight is defined like that. Then the generating function for A is A in A, weight of A. But this means A in A means A is a subset of n, and the weight is x to the A, y to the n minus A. But if you collect all the subsets of cardinality k, then the k could be from 0 to n, and the weight is x to the k, y to the n minus k, and the number of a's such that the cardinality is k is exactly the binomial coefficient n choose k. But we know from the binomial theorem this is x plus y to the n. So the generating function can be written in this way. All right, and we will see more complicated examples later. For example, A, let's say, is the set of permutations, all permutations of n. and the weight, define the weight of an element to be x to the cycle of A, where cycle of A means the number of cycles in the permutation A. Then we can show, we will prove this later. The generating function for A, which is this, can be expressed a nice way like this. Like this. And yeah, this is more complicated than the previous examples, but we can prove this. We will do this later. And so that we define generating function for a sequence or generating function for object, but we will just use generating function quite loosely, like generating function for permutations and generating function for like and generating function for like matchings and etc. But we will see many examples like that. So this is only the basic of generating function.